Ge det någon minut till bara. Så, jag tänkte köra igång. Jag hann inte riktigt med förra gången att göra färdigt Python-kapitlet när det gäller plottning och diagram. Så jag tänkte köra Matplotlib föreläsningen nu. Och efter det så tänkte jag prata om CALFEM och Python. Sorry, I switched to English again. It was a bit my mistake. So I didn't do Matplotlib last time, so I will do Matplotlib. Brief introduction to plotting library that uses NumPy. Then I will go through CALFEM for Python to just introduce you to CALFEM and using CALFEM from a Python setting. I will go through several examples very in detail so you can see the differences. And then also I will go through a very short introduction to object-oriented programming, because the exercise sheets that we are going to do this week uses a bit of object orientation. You can do the worksheets without knowing anything, but I think it's good to get an introduction to object-oriented programming before you go through the sheets. So let's start. So now we have covered how to do matrix computing with Python. And usually with matrix computing, you also need to plot data in some way, do diagrams, and also analyze data and create a visual representation of those. And there is a library that mimics the way you do graphics in MATLAB, and that is called Matplotlib. And it's a very large graphics library for Python for scientific visualization and plotting. And so it has been for a long time. It's very similar to MATLAB. Some of the modules, at least, are similar to MATLAB. There is a high-level library that you can use for doing your own plots, very detailed, but there's also an emulation layer that mimics all the commands from MATLAB. I have provided here some links to documentation for this library. There's also a really large set of tutorials for basically plotting every kind of plot you can imagine. So my introduction will be very short. If you want some more depth, go to the Matplotlib site and look at the tutorials. So Matplotlib, in the way we are going to use it, we will use the emulation layer that emulates the MATLAB plotting layer. So in this case here, we use import matplotlib.pyplot. This is the special module that has the same commands as MATLAB. And we import it to make it easier to use. We import this entire one as PLT, so we have to add PLT to all the commands we're going to use. So I'm just going to import this now. So simple plotting is done with the plot command, just like MATLAB. And Matplotlib doesn't require you to use arrays, so it can basically take any data type that you can access with indexes, and those you can plot. So in this example here, I have a list of 4 values, 1, 2, 3, and 4, and I can plot those like this. I can, of course, change this like this. The show command here is not strictly necessary if you're using notebooks, but if you're running from Spider, the show command will bring up a window on the screen. So that is important when you do it from inside Spider. Also, Spider has a special way of handling plots. So in some cases, you will also get them inline in your console. Running them outside Spider standalone, you will need a show command to use them. It's no problem to use show within a notebook either. So you can either use show or not use show. That's but if you want to bring up a window, you need to use the show command. Of course, you can plot NumPy arrays as well. So I import the NumPy library here as NP. And if, for example, if you want to plot a function, you could use a range command to create a range of numbers that is from 0 to pi, for example. The problem with that is that sometimes you don't get all the values in but because of precision it goes stepwise, you can miss to get the final value. So if you want to make sure that you get a series that starts from 0 and goes and includes 2 NP or 2 pi, you need to use the linspace to generate a series of numbers. In this case, you have the starting value, the end value, and how big the array should be. And then linspace will interpolate that. And here you also see that you have a sinus function for NumPy. And the NumPy sin function can take arrays as input. So in this case, when you put an array into the sin function, it will return you an array with the same length, but with that each value has the computed sign value into it. So let's see if I just add a print command here just to see how they look. So you see here, I have the x value goes from 0 to 2 pi, which can be okay. And then this is the y array, which is computed from by executing sinus on each of the values in the x array. Plotting these is simple. So if you have x values and y values that are correspond to each other, you just plot x comma y. In this case here, it plots a nice sine function here. A common option that you need to change is kind of you want to have different lines in your diagrams, and this is exactly the same command line structure you have in the MATLAB plot command as well. So you have the x values, the y values, and then you have an attribute parameter here which controls the appearance of your plot. So in this case, I want red dots and circled lines here. So now I get just dots. If I want to have a blue line with circles and a line between them, I can do B, which stands for blue. O stands for that I want to plot circles, and this means that I want a line as well. Let's see if I just change this to this is a blue line. I'm going to add a circle to that one. And if I want a line that is dashed, I can use 2 dashes like this, and the line will be dashed. I can also have crosses instead of circles, and I have a plus sign here. Crosses, I can also combine this with, so I can have a green cross with lines between them, like this. So now you see there is a line here between each cross. You can also do multiple, I have to change it. This should be linspace here, with 0 to 100 values. Now in this case, I want to plot multiple values. So in this case, I want to plot the sin function and the cosinus function. And then I can do from 0 to 2p, 100 values, and then I calculate one two y values, y1 and y2. This. And then I can plot multiple lines in the same diagram by specifying x, y1, and then the attributes for this line. So red line, x and y2, and the blue line, and a dash here for that this should be connected. And now you see it plots both of them in the same diagram. There are much more properties you can change. You can probably look them up in the documentation as well. There is a multitude of different properties. And properties other than those the line attributes, you can also specify them as command line arguments, like keyword arguments. So this is a keyword argument. Line width 4.0. That means that I want the lines to be 4 pixels wide. Now see here the lines are wider. But if I want to specify the lines separately, I need to somehow get access to the different lines in the plot. So in this case, you can, when you the plot command can return objects from the plot command. So if I want to have each of these lines as an object, I just put line 1, line 2, and then assign them here in the plot command. So line 1 will be the first line here, so the line with these parameters. Second one will be line with these parameters here. Then I can access them because this is a Python. Everything is objects in Python, so you can access methods on objects. So each of these lines has a property here called line width. You can call with set line width. And then I say for the first line I say 4.0, and the second line I have 8.0 as the line width. Now you see here that the second one, the blue line here now, is thicker than the red one. It's also possible to get, so if you have multiple lines, more than 2, if you assign one single variable, you will get a list of all the line plots in your diagram. And that can be beneficial because you can set multiple properties on multiple lines at the same time. So in this case here, there's a special function called setP, which stands for set property, which can take input as a list of objects, and it will assign each of these objects the corresponding property line with 8. You can also plot multiple figures. So using a notebook is perhaps not so common, but you can, when you have standalone programs that you run on your desktop, you can create figure windows that are standalone from each other. So one plot in each window. You do that with figure 1. This command tells you that I want to create a new window for my figure that is with index 1. Then I have another window with index 2, and every time if I call this command again with figure 2, the active plot will, the output of the plots will go to that window with that number. Now you see I have 2 plots instead of 1, with the y1 in the first one, red line, and the blue one in the second window. So running this on a desktop machine will produce 2 windows on the screen at the same time. You can also divide your windows into several subplots. For example, if you want to compare data together, you can have 2 diagrams on top of each other with the same axis and then different y-axes to compare. In this case here, I have there's a command called subplot, which has a bit odd syntax. So you give it a number that consists of 3 positions. So the first one is the number of rows. The second one is the number of columns, and the second one is the number of the plot. So in this case here, I have a subplot with 2 rows, 1 column, and this is the first plot. Then I have a second plot. It is subplot with 2 rows, 1 column, and this is the plot number 2. So then this is a one plot that combines with 2 subplots. So running this on a desktop, it will produce 2 plots, 2 plots in a single window on top of each other. You can also have, I have 1 row, 2 columns, plot number 1, 1 row, 2 columns, plot number 2, and this will produce plots next to each other, so like this. So up to now we have created just basic plots. They're just containing simple. There is no titles, or there is no units or anything on the plots, and you can provide that as well. There are several commands for doing this. So in this case here, I have there's a command function called xLabel, which you can provide a label for the x-axis, and ylabel, which you provide the label for the y-axis. And the result will be like this. So in this case, I have x here, y2, and y1 here. Another cool thing you can do with plots Matplotlib is that you can add text to specific positions in a plot. So there's a text command here, and it takes the x and y coordinates as the first arguments here, and those are in the plot coordinate system. So you need to kind of specify the position of the text inside your plot coordinate system. So in this case here, I plotted on a x position pi divided by 2, and at the y position 0.8. And then you can specify LaTeX notation here to provide formulas in the plot. So it's quite powerful text interpretation in this. Horizontal alignment means that it centers the text around the point that you specify. Let's see what happens if I run this. Now you see here that the function I specify here appears at 0.8 here, centered here. If I put 1.0 here, it should be on top of the plot axis here as well. And I can do left. I can do right adjustments. There's also a vertical parameter you can set. There's also a way of actually putting arrows in your plot. So, for example, if you want to point to something interesting, if you want to point to something interesting, you can use the annotate function, which is similar to the the text command, but it provides you with a way of setting a position for the arrow, so the starting point and an end point. So in this case here, you have a start point here, and where the text should go specified here. So you have this in pairs like this, or it's called tuples in Python. And then you can specify the properties for the arrow here in this case. Let's see how it looks, and we can change the arrow here. So now I'm pointing my arrow at this position here. And all the text goes here. So if I put that, for example, on 0, the arrow will become longer. And I can do so look at see here. So you can put a margin around this here so that it doesn't go all the way in here. So make sure that you have space for your plot. That's a useful function if you want to plot and show something in your plot. You can also specify the boundaries for your axis using the xlim and ylim commands. So here I say that x should go from 0 to pi, and y limit should go from 0 to 1.0. So I mean I zoomed in on this part of the curve. So I can also do, for example, from 0.5 here. Quite useful if I do a pi divided by like this. So there's also a way of zooming in on interesting parts of your plot. You can also change the scaling of your axis using the y scale and x scale functions. So in this case, I scale my y scale as a logarithmic scale. Then you see it's linear. Also quite useful. You can also do some other plots that are built into Matplotlib. So you can do histograms, and then you do here I have a random distribution. Basically just and then you can sort it into bins, and you can have different number of bins here as well. Here, if I can do it. If I have 20 bins, it will increase the number of value ranges. It will sort the values in. Bar charts, probably more domain of Excel, but you can do these in Matplotlib as well. So it takes X values and Y values. Now I have Y values is just random values here, and then I just assign a range here from 1 to 20. So now you see here it creates a bar plot diagram like this. You can do scatter plots, basically displaying X, Y values, and then also scaling these by a certain, for example, here I have X and Y, and then I have a scale here to scale these different points with a certain amount here, which is scale command here, our property. Here I also use alpha here, which makes them a bit transparent. So if I have 1, 0 here, they are non-transparent. You can do contour plots. This case here, I create 2 linspaces. I create a grid here from -6 to 6 using 100 points. And then you can create something called a mesh grid that creates a grid from 2 linspaces. And then you can use a normal function here to calculate a C value in each grid point. So in this case, I take the sinus function of X times Y, and I plot these using a contour plot. And there are two variants of this you can use. You can use contour F, which creates a filled contour plot. Basically, it fills out the spaces between the ranges. And then you have contour, which just makes the contour lines. You can also display images. So I talked a bit before that Python has a lot of built-in functions in its runtime, and you can so before you invent something yourself, you can probably find a function that you can use to achieve the result. For example, in this case, I want to download an image from the web. There is a special module called URLlib and request, which can download something from the web for you. So in this case here, it retrieves a file here and stores it in my home directory as 6502 JPEG. And then I can read this file using the image read command of Matplotlib. And it can display an image like this. And here you can see I can also turn the axes of my diagram off. So I don't show X, Y, just show the image here. If I have on here, you will get the axis here, basically the pixels here from 0 to 1008 or something, 1600 here. And off, like this. You can also change or control how the images should be interpolated. So if you have a very image with very few pixels, you can tell Matplotlib to interpolate between the pixels so it gets a bit smoother in this display. It's basically shown in explanation here. So here you can see that you have the nearest point that just takes the coordinates from the nearest pixels, but then it can also interpolate between the different pixels in different ways. So there are multiple ways of doing this smoothing of coarse images. Perhaps nothing we're going to do in this course here, but it's kind of useful anyway. Streamline plots is when you want to plot a field of some kind. You can do this here as well. So here I have X, Y coordinates here. I have a UV. I create the speed, the sizes of the arrows, and then I can do plots like this. Could be useful for finite element plotting if you have that need. Bar charts we covered before. You can also do 3D plotting. So I showed you 2D plotting of grids. Those can be plotted as a 3D plot as well using the plot surface command here. And the output will look like this. And if you're running this standalone, you can get the images in a window which you can also rotate around. So that was Matplotlib. It's just a short introduction. So the CALFEM examples you will be using in the worksheet will be using Matplotlib for the plotting. So that's why I'm introducing you to this now. And you can also, Matplotlib plots can also be integrated in the user interface library that we're going to use later on called Qt. So it fits nicely into this course. So, CALFEM. So, probably most of you have probably seen CALFEM for MATLAB before. And this course has, from the beginning, actually started with a different language called Fortran. It went from Fortran to Visual Basic with Fortran and Delphi. And we finally decided that we needed the user interfaces was most easily implemented in Python and Qt. So to create a finite element program in Python, we realized that we needed a library that was very similar to CALFEM, and also so that you feel familiar in implementing CALFEM as you can use your knowledge from previous courses in Python. And it's very, very similar. So we have something like 90% of the function in CALFEM implemented in Python. It uses NumPy for matrices. Wherever you get the output as a matrix or array, you will get that as a NumPy array or matrix. You can also use lists for some of the simpler parts like element properties. So it's very similar. In some functions we have changed to, because it's impossible to implement them syntactically exactly like in MATLAB. So in those functions we have, I will show them later on also, that they're a bit different, but it's very few places. We have also added to CALFEM for Python extremely powerful mesh generation tool called GMSH, also triangle, but GMSH is the one very powerful mesh generator, which is integrated in the Python commands. So you don't have to know anything about Gmesh to be able to do meshing in Python. You just install a library and it will do this for you. Plotting is done in Matplotlib, as I just went through. So it's a hopefully very useful library for coding smaller finite element applications in Python. It's divided, it's a bit differently designed as the MATLAB CALFEM, because in MATLAB you just put the search path in a directory and everything is available as separate M files. CALFEM for Python is divided in several modules. So you have a core module that contains basically everything that is not graphical. So you have all the element routines, all the system routines for doing things with converting coordinates and extracting element displacement and so on. This is part of the CALFEM.core module. We also have a CALFEM.utils, which contains several I/O routines and other miscellaneous routines. Then we have one or more those related to the mesh generation. So there's a module called geometry, and this geometry module is where you describe your geometry that you want to mesh. So there are several commands for easily creating geometry with holes and with splines and lines. And that geometry you can then use with the CALFEM.mesh module, which will take that geometry and generate the topology, the element coordinates, everything that you are used to from CALFEM. So you can take that mesh, the element information, and assemble your finite element problem. And then we have CALFEM.vis and CALFEM.vis.mpl. So the vis first one is can only be used when you're running on your desktop, because it uses a special visualization library called visvis. So it will bring up windows every time you plot something. CALFEM.vis.mpl can be used in notebooks, but also standalone. So it's also something that we have added recently, because the visvis library is kind of on its way out. So here you visualize your results. So to use CALFEM, you need to, I have probably put that in the instructions here. You have to open a CALFEM prompt. I have a question here. Let's see here. You had a question? I have a raised hand here from Weirs. Yeah, if there is a difference between MP arrays and matrices, yes, not so much. So basically, a matrix is a specialization of an array. So where you have an array, you can use a matrix, but the matrix contains operators for using it. If you want to do linear algebra expressions, you can't do this with arrays. You need to use the matrix data type, but they are derived from the same base array data type. Okay. So told you I think it's written in documentation that you can install CALFEM for Python from the command line. You open an Anaconda prompt and you type pip install CALFEM for Python. So I'm going to do this here in my notebook here as well. So if that is, well, you should have a lot of commands output here. So I will kind of demonstrate CALFEM with examples. And I will go from the extremely simple to the bit more complex. And for the next lecture, the next lecture will cover mesh generation. So I don't think I will do this in this lecture. I will give you some time to recover, not too much at the same time. So the general procedure for FA calculation, you probably have learned this in the previous courses. You define your model, you generate your element matrices, you assemble those elements into a global stiffness matrix, you solve the system equations, and you calculate element forces. So here I have a very simple example of a system of springs. I have one spring here connected in serial to a spring with K and a spring with 2K stiffness. I have these degrees of freedom here, 1, 2, and 3. So first we load all the necessary requirements. So here I load NumPy. I also load CALFEM core as CFC. So in all examples, I use this prefix CFC for the core, CFV for the visualization commands. And here you can also switch between vis and vis MPL. As long as I don't change this one, the example should work. I also need a math library here. So let's see if we import this. So first thing we do is we create an EDOF, which is similar to what you do in CALFEM. Now, you can't create arrays quite as simple as you can in Matlab. You need to create an array. And in this case here, I have an array with 3 elements, 1, 2, 3. And one thing we decided that is a bit odd for Python is that degrees of freedom in when you do assemble and you do boundary conditions are 1 based in this case. So you can use all the same examples as in Python or in Matlab in CALFEM for Python. So just note, degrees of freedom are still 1 based. So the commands will handle it internally. Only exception is if you assign the F vector, for example, the force vector, you need to specify that index base because then you're accessing the array directly. I have a question from Sarah. Yes, go ahead. Yes. Column, yeah, I know. We also decided to make changes in the EDOF matrix in CALFEM for Python. So in MATLAB, you have the element number as the first column. We don't do that. So in this case, we only specify the element degrees of freedoms, no numbering. I think we decided it was a cleaner syntax than having this number. You could solve the numbering in different ways anyway. So that's why that's also a difference. Let's see here clear. So we have an element going from 3 degrees of freedom from 1 to 1 to 2, 2 to 3, and 2 to 3. So these 2 elements go from the same degrees of freedom. Next, we create our matrix and force vector. These are just, in this case, I created them as matrices. I don't think there's a really requirement that they should be a matrix. So I have now we have 0, 2, have a global stiffness matrix that is 0. I have a F vector that also is 0, like this. Then we do our element matrices here. So I usually kind of try to put constants for different element properties so that they're easily changeable in one place. So in this case, I have a constant here, K 1500, and there's an EP1K, and then EP2 2K. And then the element stiffness matrix is, there is an element routine called spring 1E, which takes EP1 as input. Then we have KE2, which takes EP2 as input. It looks like this. Does it make sense? And then we need to assemble these into this global stiffness matrix. So now we use a very similar way of doing this as in CALFEM for MATLAB. So you take the first row of the EDOF matrix as that is the degrees of freedom it should be assembled to. You give it the K, a global stiffness matrix, and then you have the KE element matrix. And here is the first difference from CALFEM for MATLAB. I have a question here about about arrays and matrices, and I think you can do it interchangeably. So you don't, it doesn't have to be a matrix, and also. So CALFEM is not designed to be super efficient. It's more designed to be more educational tool. So we haven't optimized these routines very well. You can also, this is also a way of, you can do this by yourself as well. You can also have a different solving algorithm. So it's, you can do it manually as well. So it's up to you, but we provide you some of the functions that are available in CALFEM here, so it makes it easy to use. I will try to change it to an array type, and we can see if it works. Okay. So let's see. Assemble these here. Yeah. Also, I said that the difference here that in the MATLAB version, it returns you K, K, F here on the left side, because arrays can be accessed and modified in place. We don't return it to the left side here. We can actually, this command will actually modify K, the values inside K directly. It's a bit unusual for Python to do this, but this works here. So there is no need to have this K, F on the left side. Now let's see if I change these to array. Let's do they are similar here. Let's see. So apparently you can do both. Now we have our global stiffness matrix. We need to solve our equation system. We need to create a boundary condition array. So in this case, we have boundary condition on degrees of freedom 1 and degrees of freedom 3. And on the let's see, if we go back here, we have a force here in the position 2. And here I put it in position 1 because this is a number array, and the degrees of freedom are starting from 0. So here in this case, this is the exception. Here you have to put 1. It should be 2 if you use MATLAB. This is 1 here. And then we have the solver command, which is very similar to, it's actually similar syntax as for MATLAB. The only thing here that we don't have a single array for the boundary conditions. It's divided in two. I will, regarding the coordinate matrices, I come to those later. In this case, we don't have any coordinates at all because there are springs, but I will get back to that as well. For the boundary conditions here, it's divided in two. So the first part is an array with the degrees of freedoms which are prescribed, and the second part is an array with the values that are prescribed. So if you only provide the first array here, it automatically sets those degrees of freedom to 0. So if you want something that is non-zero, you have to specify an additional array with the values for those degrees of freedom. I will also get back to that later. So let's see here if it works. So it seemed to be okay. So you have 0 here on the first one and 0 on the second one, and then a displacement here for this one. And the sum of these should be 100. So that also seems to be correct. Then you can extract the element displacements here, which is the forces in each spring, like this. Okay, so let's have a 15-minute break, and I will get back and continue with the examples here later on. Okay. So I just okay. Let's continue. So for the next example here, I will kind of increase the complexity. So now we have truss here with 3 elements. We have 8 degrees of freedom, so degrees of freedom 1, 2, 3, 4, 5, 6, 7, 8, and 3 elements. We also have a force here that acts on this node, and it's 1.6 meters and 1.2 meters high. So it's the same example you can find in the CALFEM manual. Okay, so first we start with a Eadorf matrix. As I said before, it starts with 1 as the first degrees of freedom. So 1, 2, 5, 6, 5, 6 to 7, 8, this element. And the third element, 3, 4 to 5, 6. We create matrix and load vectors. Sorry, the global stiffness matrix and force vector. As before, I put all my constants here in the beginning so I can change them easily later on. So I have elastic modules, I have areas here, and I have element properties 1, 2, and 3. Here I also specify the element coordinates, so EX1, 2, 3, EXY, 2, and 3. I will show the common example. We'll use a different approach for generating element coordinates, but in this case we generate them specifically for each element. And then we need to create element matrices, in this case KE1, KE2, and KE3. And then we assemble them into the stiffness matrix one by one. Here we have prescribed displacements on 1, 2, 3, 4, and 7, 8. They're all prescribed to 0, these points. We have a force at degree of freedom 6. In this case, we need to specify 5 because we have a 0-based array, minus 80 times 80,000 newtons. And we solve, and it's only degrees of freedom 1, 2, 3, 5, and 6 that will have displacements here. So this node will move. All other nodes will be 0, which can be seen here. And then we have reaction forces on all of them. except for the ones we prescribed here. Then we calculate the element forces, and there is a special command called extract LDISP, which extracts the LDISP from the EDOF and the global displacement array, and stores them for one for each element. So in this case, it's ED1, and then we can use that in the bar2s command here as input, which takes the element displacements and calculates the force in the bar. Okay. So when the examples get more complex, we need to handle the coordinates and the element coordinates in a better way. So in this case here, we have a bigger truss here with 6 nodes and 12 degrees of freedom. And the node, the element arrangement is like this. We also have a force directed 30 degrees down, and we have areas on all the bars the same, and also an elastic modulus that is same for every bar. So in this case, we have an EDOF matrix like this, a bit larger than before. We create our global stiffness matrix and force vector. We set our global constants here, A, E, and our element properties to E and A. Here we have an array of element coordinates. So since we don't specify an element coordinate for each element because it starts to get impractical here. So we have an array here with each row is element coordinate. So, and then we have an EY as well for the Y coordinates of the elements. So now we have all the prerequisites to use a loop instead of doing the assemblation element by element. And to handle it inefficiently, we use the zip function here to combine, we loop over EX, EY, and EDOF. And that will assign the current element X coordinates to ELX, and the element coordinates for Y in ELY, and the topology for the current element in LTOPO. And those we can use here to create our bar2E element matrix by specifying ELX, ELY, and the element property here. Then we can directly assemble it into the stiffness matrix here, like that. So now we have to solve the equation system. So we have prescribed 1, 2, and 3, 4. They are all zeros because they are in the wall here. They are fastened here. So then we specify 1, 2, 3, 4 here in the BC variable. For degrees of freedoms, let's see here. It seems, oh, so 12 and 11, that should be, yeah. Yeah, it's 12 and 11. So these are decremented ones. So they should be 11, 12. And I just calculate the components for these and apply those in the force vector. And I solve the equation system here. So now there's another command that you can use called extract LDISP, which creates the element displacements from EDOF and A global stiffness or global displacement array, and assigns creates a ED array which each row is the element displacements. So I have a question from Sarah. Yes, there is a PDF CALFEM manual, I think. I'm not sure, but I have to check. If there are, I put that on the web page on the Canvas. I just have to tell you that it's not a complete. I don't have a complete Python manual. We are working on creating a combined CALFEM and Python manual, but it's not there yet. But we have the reference manual is there. But basically, most of the other commands should be the same, so it should work. So extract LDISP will extract element displacements, and then we create an array here to store the element forces, which has the same shape as EDOF. So we have a number of elements. Each element gets one row in this matrix. And now we can do a loop for calculating the element forces as well. So we use zip here to loop over EX, EY, and ED, and store them in ELX, ELY, and ELV. And then we can use those as input here to the bar2s command and store them in NI. So we have a nice array with element forces later. So yeah, now we have completed. So now we calculate all the forces and store them here. You can also there is a second way of handling element coordinates. So if you want to have a more coordinate-based topology, we can specify a coordinate array as well. So in this example here, we have a frame which has both beams and also bars in the same structure. These are the element degrees of freedoms and elements. So here we create our global stiffness matrix, force vector, assign 12 here. There is a force here at 12 here because this is 13, but we have to specify one less here. And then we specify our coordinates here. And then you can specify what is called, it's coordinate topology instead. But I'm not sure if I'm doing this. Yeah. So coordinates here is used to create element coordinates later on here. So here we have just a list of coordinates, and we have degrees of freedoms for each of them here. First for the beams, and then for the bars. They have different bars. Only have 2 degrees of freedom. So we have created an array specifying the 2 degrees of freedom that are used for the displacement degrees of freedom for the bars. We have an element problem. We have set it to 0, 1, 0, 1 here. So we're not interested in exact numbers here. We have our element topology for the beams. And then here you can use coordinate extract here to create element X and Y values. So you don't have to specify them separately. It takes EDOF here and extracts them from the chord and uses the DOFs here to identify them. So I can see if I do. It creates degrees of freedom for the EX, Y. To assemble this, we need 2 loops because we have 2 element kinds. So we'll first loop over all the beam elements, assemble them, and then we'll loop over the bar elements here. And then we calculate everything here. So I don't want to show it anymore. I just finished this today because I thought it was good to add this here. But you can use what I wanted to show is you can use the chord extract here to extract the element coordinates here. And then we have 2 loops here, one for assembling the beam elements and one for assembling the bar elements. In your assignment, you will only have one type of element, so it's you only have to have 1 loop to assemble them. Also, when you have on Wednesday when I have the next lecture, I will show you how you can easily create EX, EY, EDOF, and all those variables automatically using your mesh generation tools. Sorry, I have to check this. Okay, but this was a basic introduction to CALFEM. I've also put the documentation links on the webpage, and also if I can find a PDF version of that as well. So what I wanted to talk about very briefly at the end of this lecture is is object-oriented programming. So up until now, we have been doing function-oriented programming, which means that you create functions and perhaps modules. You put your functions in modules, and the data is passed by passing the data to the function. So, for example, if you want to do a library for drawing shapes, you create a number of functions for drawing shapes or moving shapes, but the data structure for shapes are, for example, lists or numpy arrays and so on, but that you pass the functions to work on. With object-oriented programming, you try to combine data with methods in one single entity, and objects are usually can be described as nouns, for example, such as points, circles, equations, models, cars, you name it. Nouns are kind of the objects. And objects can interact with each other by sending messages. And these are the verbs. So, so the verbs are the methods in Python. For example, an object has a method. To communicate with an object, you call a method on the object. And the method is a function that you can tell the object to do something. So you have the methods, and you also have the properties that describe the objects. That could be, for example, coordinates. It could be, if you have finite element, it could be the elastic modulus for a problem or model. That's the difference. So just to illustrate the differences here. So I have created a module here that can handle points in different ways. So I need to kind of be able to move a point. I need to be able to zero a point, and also need to be able to set a point. So I decided that the data structure for the point should be a list of x and y values. So I have a function here that creates a point. So basically that returns a list of the point values. And I have a method here to move the point. So and the input here is the point to move, and the delta x and delta y of the point. So in this case, I actually increase the x position here by adding dx to the first item in the list and the second item in the list. I have a 0 point function here that zeros my point. So basically it sets it to 0.0 and 0.0. I have a method called setPoints that takes the point and has the parameter x and y and assigns the points in different ways. So why this? The idea here is that by doing this, we can kind of, the user doesn't have to know anything about the actual implementation of the data of the point. So using this function here, I can create a point without knowing what it is. I can set the point, I can move the point, but the data is still separate from there is no objects. It's just a set of functions that can manipulate points. So I just define these here. So to create a point, I call my createPoint function. And you see here that it prints out my position here. But P here could be anything. It could be any data type you select. So it could be in a database or something, but you use the point to create the actual data that I want to manipulate. I can move the point. Then I have to specify my point here, and I have a method that actually works on the data and adds 3 and 2 to this point. I have a method called setPoint, which sets the point to something. And I can have also a print point here to print the point. So actually it should perhaps be better to do this. So now I created a module here that can work, so you hide the details of the actual data. You return the data to the user, but the data has to use this P to always with your functions. So to combine these to a single data type or a class, you need to so to create objects, you need to kind of have a base model or a description how this object should look like. And in object-oriented programming, the description of classes or description of objects are defined by using classes. So in Python, you can describe a new object by using class, the name of your new new object, in this case point, and you also need to have a way of initializing your object in some way when you create it, and that is done using this definition init function here. So this class will have two properties, x and y, that are 0 from the beginning. These are also called instance attributes, and those will be unique for every object you create. They will have their own x and y. So in this case here, to create objects from this mold, the class mold, in Python, you do like this. And it's also called instantiating. So P here is I want to be a point object. And Q is also a point object. I forgot to define it like this. And then like this. So. So when I do this, what happens is that this will call the initialization method of the object and create these variables inside the object. So self here means that it refers to the actual object reference in memory. So this is the way you can describe this in a class description. So when you actually create the object, self will be replaced by the actual memory of the object in memory in the computer. So every time you create a new one, self will be different. But in the description here, it will always be the same. So when you do self.x equal to something, you create a variable that is attached to this new object. So if I print out here, you see that now they're all 0. I can change the attributes by assigning them directly. And you see here that every object has their own instance attributes. So when I assign x and y on the P object, it doesn't change the Q object. So Q owns its own data. So now you have a data that is connected to the object. So just the disclaimer here. So if you have seen other object-oriented languages, you often access the instance attribute by using get and set methods. So in this case, and also the idea of object-oriented is that you should hide the implementation details from the user. And in this case here, I actually explicitly make the instance variables available to Python directly, which is not true encapsulation. But this means that this is not a problem, which I will explain later on in this lecture, that you can actually live with this a bit more. But first, we implement it in the correct way. So we want to hide these attributes from the user, so the user will not be able to access these variables directly. And the one way of doing this is actually, if you prefix a variable in Python with double underscores, you can't access them from outside when you create the object. Those are internally to the class, so they are private. So in this case, I have class point, and instead of having x and y here, I have underscore underscore x, and assign them to the incoming variables here, like this. And then I also add parameters here too, so I can assign them when I create the object. So in this case here, I redefine my object like this. So let's say what happens now if I try to access these x and y attributes. No, so point doesn't have no attribute x. So now we have hidden these. The object still stores these values, but you can't access them from outside. So we need to create a method to access these attributes for the user. And you can also not access the underscore attribute like this. So they're basically hidden from us. What we can do is we can provide a set of methods to the class that enables us to access these variables. So for example, if we want to assign the value, we can create a function called setX that assigns the underscore under x, the x value here. Same thing with the set_y. You can also have a convenience version that sets both of them at the same time. So we redefine that, and now we can do like this. So we have we can set 2 by 3, set x, y, and x3, but we can't kind of see the values. So now we can set them, we can't access them to read them. So what we can do then is we can add x and y values here, functions that just returns the values like this. So now we have a way of accessing the methods, but now the user can't touch the internal implementation of the values inside the object. So we could have implemented, instead of using internal variables, we could have implemented database access. So the data could be stored on a database server somewhere, but you still access the point in the same way. So the underlying implementation is hidden from the user. But it's much more complicated to use this kind of notation. So Python has added something called properties to its object-oriented classes. And properties is a way of hiding the data, but giving you the same convenience as assigning attributes directly. So now I changed the the x, y functions to get and get y. And what we can now do is we can define properties. So here you see I have x equals to a property, get x, get y. So this first here tells what happens when this property is read. It will call the getX method here, and when you assign x, it will use setX. So now we have our point here, and we can do this without and still enable us to have encapsulation. So when x is assigned 42, it will call setX. Same thing with y, it will call set_y. And if we read the data, it will call getX and get_y. So let's see how we run this. So you see, first it calls setX with this one. It calls set_y, this one. It will call getX here to get the x value, and then it prints it out. Get_y and prints it out. So now we have hidden this inside a class in a very nice way. So what that means is that you can start implementing your objects with normal attribute variables, and when you need to protect them, you can add a get and set method and a property to protect that variable. So we also need to be able to move our object now. So we for the function-based ordering, we have a move property, and so we add a move function here, or method to our object. We specify dx and dy for how much we should move it. And you also see all these methods for an object has the self as the first argument. And when you create the object, you never have to call the method with self. That is automatically inserted by Python, and it will insert the actual object as a parameter automatically. So self_x, I just add to it. Now we can work with it like this. So in this case here, we have create two objects, P0 and P1. We can do p0.move 10, 20, move -5 and -5. So now you see the result here is a position of 5 and 15. You also see here, so the actual argument to any of the calls here will be this here. P0 will be self when you call it. That's how it works. So another method that could be nice to have is be able to copy from. For example, if you have create a new object and you want a new object to get the same position as the old one, you can have copy from here. So in this case here, I have this one here. P is the incoming object, and then I assign x p.x self y.p.y. So if I have a more complex object, I can assign all the attributes here. So here I have the same example here. I create p0, I create p1, I move p1, p0 and p1, print them, and I let p1 copy from p0, and that should be the same as p0 then later on. So you see here, p0 is 10, 10, and then in this first is from -5, and then I let p1 copy from p0, and then it's the same coordinates as p0. Python has some special instance method that you can implement to achieve certain effects. So in this case here, I have we have already seen one of them. This is init. This is a special method that's called when you create object. There is also a method called str, and that is called when you print an object. So for example, if you print point, it will work, but what happens here is that it will, so every object in Python inherits from a default object class. And that class has all the methods, a basic implementation of all these special methods. So for str, there's the default implementation that just prints out the memory location of this object. So if we want to have it nicer, we probably wanted to print the actual position of our point instead of this huge pointer array here. So what we can do then is implement this str function here. And what you do is you return a nice output of your object here. So let's see what happens. So in this case, I assign 42 and 84, and then I do print p here now. And now you see here, it prints out point in a better format like this. So by using str, you can actually make it print out in a nice format instead of an encrypted memory reference. Also, every object in Python is a class, or is derived from some class. And every new class you create behaves like normal Python objects. So they are you can handle them using the same, you can store them in lists, you can store them in variable references. So for example, here, I can create a list of points. So in this case, I have create an empty list like this. And I create points by adding them using the append method. Point, and I create random numbers, random points here, and assign them to this list. There's also a shortcut of doing this in a single line. For point random for I in range 10, this will create a implicit list, it's called. But what is nice now is that you can actually loop over these points like you normally do with your Python. You have 4p in points and print p. So now you see you can ask the point to print itself, and it will print itself nicely like this. Also, when you create Python your own objects, variable references will work just like variable references like normal objects in Python. So in this case here, I created P0 and P1. I assign P2 to be 0, 1, P3 to be P1. And you see here now they reference to the same object. So basically, P2 is equivalent to P0 and P3 is equivalent to P1. Another nice thing is that in object-oriented program is that you can, we've already seen that with the object, that every object is, a class you create is inherited from this basic Python object called object. So that means that even if you don't provide any functionality, a large functionality of your class, it still has some behavior that you can use it like an object. But you can do this yourself. For example, if I want to create a graphics library, and I have a lot of different geometric shapes I want to implement, I can create new classes that uses the base functionality of point, for example. So for example, I want to create a circle, and a circle has a position. So I could derive circle from point, but then I get all the functionality from point in my circle. And this is done by inheritance. And you define a class that inherits another object by specifying a class, the name of the class you want to inherit from, in this case, point. You create an init method for the new class. And one important thing here is that you need to call the init method of your inherited class. Otherwise, it will not create the necessary data for your inherited class to add that to your own class. And that you do with this statement here. Super, that means call my inherited class init method with the parameters x and y. So for my circle, I provide x and y as the parameters here. This means that they are the default values. If you don't specify these arguments are 0. And also I add an initial argument for the radius of the circle. So here I call my point, and then I initialize my, fix this here, my radius here as well. So self radius equals to r. I add a set radius and a get method here to be able to access my radius attribute. I implement a copy from here, and you see here I call my super copy from, because I need to copy the data from my point object, and I then do my copy for the self radius here as well. And then I add a string method here for printing out my object as well. And then I have my property r here to implement my radius property. So now we're ready to use the class. So now I can create a point. I missed some underscore here. So I create a circle and I create a point, and I set my radius like this. But now I can use the move method I had for defined in my point. It's available in my circle class as well. So I can reuse stuff I already implemented in my derived classes here. I can also use print at the same thing here. So it prints out, it knows what object it is, and it calls the correct method here to print it out as well. So that's quite convenient. And this is usually, I will show you in the lecture about user interfaces as well, that this is user interfaces in Windows or Mac consist of buttons, objects, checkboxes, windows, frames, a lot of controls. And it lends it very nicely to object orientation. You have every control has many shared properties that you can modify and change. So it is you can see that the uses of object orientation there, because you have such many components that share attributes among themselves. There are also another class called composite classes, which is also a very common class. For example, if you have a car consists of 4 wheels, that is typical composite class. That wheels are classes that doesn't inherit from the car, but the car consists of several wheel classes or objects. So a typical class that is a composite class could be a line, and the line has goes from 2 points. So then it owns 2 point objects. So here, as in my init here, instead of creating coordinates, I create P0 and P1, which are points, are existing points from our existing point class. I add 2 methods here: get P0, get P1, and a set P0 and a set P1. I print it out here. Now I actually use their own print methods to print out themselves here. And I have 2 properties, P0 and P1. And here you can decide if you want to write a set property here, because if you set P0, it will replace the instance or object of P0. But you can also change the P0 without actually overwriting it by accessing the methods of the built-in object. But that is a design decision. So this is how you can use a line object. I need to define it first. So line, and then you can access line P0.x. So that this will access the x property of the point P0 object. Same thing here, and then you can change the object, change the position of the line like this. And here I assign a P0 a new point as well. So here you can see you have a line from 0.00 to 3.4. So in this case, if I don't do this, it goes from 0.2 to 3.4. And this will overwrite P0 object completely and replace it with a point at 0, 0. I think I'll see here. What's wrong? It should be this one here. Yeah. This first instance here, I just return this one here, and this will not work because this will there is no set method here, so that will kind of fail. But if you add the set method here, you can assign the objects directly. You can of course add a length method here to your object to calculate the length. This could also be as an exercise for your use to implement the length as a property. The final thing I want to just cover briefly is polymorphism. And that means that Python knows, depending on the object type, which methods to call to handle different things with different objects. So if the method is available in your object, Python will kind of look in the inheritance tree and see if there is a method in the class above, and then it will be called. So if you have a derived object that you haven't implemented all the methods just in that object, it will call the above objects methods. And what polymorphism means that you can handle a mix of different object types in the same way without knowing the exact data type. So for example, here I have I create a shapes list, which is an empty list, and it has I just store point, circle, line, and the number 42 in that list. What I can do there, I can actually loop over these and print them out. And now you wonder what happens. Is this an object? And we'll see what happens. So this actually works because every object or variable is an object in Python. So even the floating point number has methods to display itself. So this is actually a floating point object. And what happens when you call print, it's called print underscore str on that floating point object, and that will print itself. So you see here it will call point, which will print itself. Circle will print itself, and line will print itself. So polymorphism means that Python knows, depending on the object type, which method to call when you access print here. And you can also test here, what does 42 mean? You can actually, this is the actual meaning of printing a floating point. It actually calls the str method on the floating point number, which converts it to a string automatically. So I know this can be daunting to kind of get everything at the same time with object orientation. The worksheet will not, it will kind of tell you how to implement your object. So you don't have to be afraid that you don't understand everything at the same time here. But I wanted to give you this so I don't introduce things that you haven't seen in the worksheet. So the worksheet for this week. Okay. English. Yeah. So what you need to do is you choose what problem type you want to consider, and there is elements here for the different problem types, and also a reference problem that you should implement for this first assignment. The reference problem is a bit special because we replace this with a mesh generation implementation later on. But for this example, you need to calculate for these 4 elements. This is the first assignment. And then there is basically step-by-step how to create you structure your finite element. So there is you have to read input, you need to do the calculation, you have to present the result. Those are the major steps. And these will be defined in a class called input data, where you handle the input for your problem. You will have an output data where you store the results. You have a solver that takes the input data, does the calculation, and stores the data in output data. There will also be a report class to create a report from your results, and you will create a main program. So this is an example of how a running program, the output from a program, can look like. But most of the things are explained here, basically step by step for this week. But it requires more work this week than last week, so just be prepared for that. But we will be here on the exercises, and you will welcome to. We will try to help you out to get through this worksheet as well. Okay, any questions? So referencing works in the same thing with a Python variable. So when you create a new object, it will create the memory for this object, memory space, and return a reference to the variable. So the variable is a reference to the object. Yeah, so px will be, if it's only a floating point, it will just overwritten. So that is okay. They will not reference the same coordinates. If you px equals to 42, But if you do px equals to py, then they will reference the same memory as well. So that you have to be aware of. But usually you assign floating point value directly to your attribute, so it's usually not a big problem. If you do px equals to, so if you do like this, p dot x equals to q dot x, those will be point at the same memory location. So if you that could be a problem. But if you use yeah, I hope you understand. Okay. So if there are no more questions, I will see you, let's see, tomorrow. It will be 8 tomorrow, yes. Okay, have a nice afternoon.